All right, so this is the Unit 1 test review. Please use this video as you need to. Feel free to fast forward if you want to. You do not have to watch the entire thing. I will do my best to kind of speed through this and explain things as I go. So the first one are just going to be our scientists. Now, this is just kind of a matter of knowing the material. There's no kind of trick to this. Okay, so we're going to start with John Dalton. So, okay, he was our father of atomic theory. So you're going to have to kind of bear with my handwriting. He was the father of atomic theory. Okay, and you'll notice that our keys usually have a little bit more information on this, but I'm not going to write all that down. So this is just the gist of what you need to know. Okay, so he was the father of atomic theory. Okay, and his model was just simply the billiard ball model, so the billiard ball. Okay, so that was just basically, he thought the atom was just a sphere, just a dense sphere where there's nothing else to it, basically just a ball. Okay, and we'll get on to his postulates here in a second. He did do more, but we'll talk about that in a second. So we're going to move on to J.J. Thomson. Okay, so J.J. Thomson, he used the cathode ray. So the cathode ray tube. Okay, basically what it did is it fired charged particles from one side to the next of the tube. And when he introduced that magnet, okay, when he introduced a positive side of a magnet to it, okay, it was actually attracted to it. So that means there was something negative in the atom. Okay, so one of his big contributions is that he discovered the electron. So discovered the electron. Okay, so which meant there had to be charges that were in the atom. Okay, so his model was called the plum pudding model, or the chocolate chip cookie, or the blueberry muffin, whatever you want to call it. Okay, it was almost kind of like Dalton's, where it was a sphere. Okay, but it had these little negative specks, negative electrons all throughout it. But the entire atom itself he thought was positive. Okay, so the entire atom was positive, and you just had these little negative electrons kind of speckled throughout it, kind of like a chocolate chip cookie, kind of like the chocolate chips in the cookie. So the cookie was positive, the chocolate chips were negative. Okay, then our next guy that came along was Ernest Rutherford. Okay, so his was the gold foil experiment. And I'm not going to write it down, I'll kind of explain it, is that basically he shot positive alpha particles at gold foil, and when he did this, he noticed that most of them went through. Okay, so that means there was a lot of empty space, so his atom model had a lot of empty space. So just that already disproved Thomson and Dalton. Okay, so they thought the atoms were just big giant spheres. When Rutherford came along, when most of those particles went straight through the gold foil, that means there was a lot of empty space for it to get through. Okay, so now he's condensed it, so there's a lot of empty space, and now you have a small, dense, positive nucleus. Okay, so you've got this small, dense, positive nucleus where the protons are located, okay, and then electrons are just floating out randomly in all this empty space around the atom. Okay, so his model kind of looked like this, where now you had a nucleus, a small little nucleus that was positive. Okay, so that's where our protons are. And our electrons were just kind of randomly floating out here in this space. Okay, so we're starting to refine the atom a little bit. Okay, now what we're going to do is we're going to move on to Bohr's model. Okay, so Bohr didn't really have an experiment, okay, or experiment name. Okay, he just basically discovered that electrons had to be on certain energy levels. So they weren't randomly floating like Rutherford was thinking. They actually had to be on certain energy levels, almost like kind of like a solar system. So we have this little positive nucleus, and instead of it just randomly floating around, we have basically these energy levels that makes it look like our solar system. Okay, real awesome circles. And these electrons are just actually floating on these specific energy levels. Okay, so he refined Rutherford's by stating instead of being randomly floating about, there's still a ton of empty space. It's just they actually were on specific energy levels. Now the quantum mechanic model, that is the last one we have. This basically stated that they're not just in orbits. So not in orbits, like you would think of a solar system where it's just one-dimensional. Okay, instead, it's actually a 3D region around the atom. And that's what they basically call the electron cloud. Okay, so instead of being a nice, just flat solar system, is you have this small, dense nucleus, and electrons can be anywhere at any given time. So that's basically why we call it the electron dot model, is that these electrons could be anywhere. So here's your cloud. But they're not just one-dimensional. They're actually going forwards, backwards, side to side. So it actually creates this three-dimensional shape. Okay, and that basically led us to the quantum mechanical model. Now what we're going to do is we're going to go back to Dalton's model, or Dalton's postulates. We're going to write those down. It says, describe John Dalton's 5 postulates on atomic theory. Okay, so our first one was that all elements, elements are composed of atoms. Now, he also thought they were impossible to divide or destroy. Okay, so now we know that this one, I'm going to put a star by it, because we know that one's been disproven because atoms can actually go deeper. Okay, so he thought it was just a sphere, but then Thomson, Rutherford, they all came along, discovered electrons, protons, so there was more going on than just the atom. So number 1 was already disproven. Okay, then number 2, he said that all atoms of the same element, so atoms of the same element, are alike. So he basically thought that all oxygen atoms were exactly the same. Now I'm going to put a star by that one because we know that one's not true, because we'll get into that more here in just a second. Remember, those are called isotopes. Isotopes are atoms that have the same number of protons, same number of electrons, but it's the neutrons that make them different. They have a different mass number. That's what an isotope is. Okay, so that one has been disproven. Then number 3, it was atoms of different elements are different. So atoms of different elements are different. Okay, so that makes sense. Hydrogen is not the same as oxygen. That still holds true to this day. Okay, then we go on to number 4. Atoms of different elements combine to form a compound. Okay, an example of that would be like something like H2O. Okay, you have 2 hydrogens come along and you have an oxygen come along, they combine to make H2O. Now he also stated that there had to be a whole number ratio, meaning you're not going to have 1.5 hydrogens and 2.6 oxygens. They have to be in whole numbers. You can't just split up an atom like that. Okay. Then the last one, number 5, is in a chemical reaction. So in a chemical reaction, atoms are rearranged and combined. So that basically means is when you have different compounds come together, they can actually switch partners and things can be moved around and combined. We're not going to destroy anything or create anything really new. We're just switching things around. Okay. So now what we're going to do is going to move on to number 3. It says describe the 3 subatomic particles of an atom. And what we mean by that is your proton, your electron, and your neutrons. Okay, where are they located? Okay, so your proton is in the nucleus. Okay, and also your neutron is in the nucleus. Okay, your electron is actually in the electron cloud. I'm just going to abbreviate that, the electron cloud. Okay, the charge of a proton is going to be positive, electron is going to be negative, and neutron is going to be neutral. So I'm just going to put, you can put neutral there, or I'm just going to draw, well, that doesn't really work. Let's fix that. Okay, we'll just put a 0 there for neutral. Okay, now by size, what I mean by this is how are they relative to each other as far as the atom goes. Okay, now what makes up the bulk of an atom is your protons and your neutrons. They make up the mass because your electrons are incredibly tiny. Okay, the way I explain this is think of it like your body is your protons and neutrons, and one of your hairs is your electrons. Okay, so if I lost a hair like that, it's not going to really affect my mass. So it's very small. So what I mean by size is that protons are very large. Okay, neutrons are very large. Okay, and electrons are very small. Okay, your mass. Okay, so what makes up the mass of your atom is your protons and neutrons, and we call that, so 1 atomic mass unit, or 1 AMU. Okay, neutrons also have 1 AMU. Okay, and electrons, you can put negligible. That just means that it basically does not matter. Okay, it has mass, but it's so tiny, like if I lost a hair on top of my head, it would not affect my overall mass. Okay, so moving on to part 4, we're just going to talk a little bit about this. Your descriptions is atomic number is your first one. That is your number of protons. Please make sure you know that. It is always your number of protons that determine who you are. If you change the protons, you are no longer that atom. So if I looked up like carbon, and you look up the atomic number, it would be the number 6. It has 6 protons, that is it. You cannot change that, it will not change. Okay, now the isotope, that's, remember, we have different number of neutrons. So protons are still the same, it's your neutrons that are different. So if I had something like uranium, okay, I have uranium-235, atomic number is 92. Now, what if I also have another uranium, and I have 238, okay, and my atomic number is still 92. Okay, so I'm still uranium, it's just my neutrons that are different. So my uranium-238 has 3 more neutrons than I do have in the uranium-235. Okay, which leads to our decay is just because we start adding neutrons doesn't mean it's always going to like to stay that way. It can become unstable. Okay, now our mass number, that is just protons plus neutrons. So remember, those two things make up the bulk of your atom's mass. Okay, so if I have something like chlorine-37, so we're going to say chlorine-37, and the atomic number of chlorine is 17. If I want to know how many neutrons there are, if my top number is my protons and neutrons, and my bottom number is my protons, all I got to do is subtract top minus bottom. So 37 minus 17, and that gives me 20 neutrons. That's all you got to do. Just please make sure you always have the big number on top. Otherwise, you're going to run into a negative number, which will create a problem. Now, this is probably the big confusion, is the average atomic mass. Okay, so mass number, it is okay to have a number like this 37. It is okay to have something different than your periodic table, because your periodic table number, the one that has all the decimals on it, that's your average atomic mass, which is the average of all the isotopes of that one atom combined based on their percentage in nature. Okay, so average atomic mass is the average of all isotopes for that atom. So for that atom. Okay, so carbon, so I can have something like carbon-14, and that's totally okay because my average atomic mass would be for carbon would be 12.011. Okay, so that decimal number is the average of all the carbons in nature. The closer you are to that number, okay, so if I had like carbon-12 and my average is 12.011, that would mean that most of my carbons in nature are going to be carbon-12. Now, if I had something like carbon-14, that's starting to get a little further away from my average, so that means it's not as common. It's okay that it's carbon-14. Okay, you can have differing isotopes, so don't feel like you always have to use this 12.011 because that's just the average of all of them. Okay, now an ion, this is atoms. Oops, my pen started messing up a little bit. Let me fix that. atoms that have gained or lost electrons. Okay, it means you have a charge. That means you lost some negatives or you gained some negatives, and now you have an imbalance in charge. So what I mean by that is you see a charge like this, so like Mg with a +2, okay, or bromine with a -1. Okay, so that's what we mean by an ion. Now the two different types of ions are your cation and your anion. Okay, so that means, so a cation means you're positive. Okay, that has a T in the middle. That's why I remember that as a T in the middle. It looks like a plus sign. So that's a cation. So if you're positive, that means you lost electrons, which should make sense. If electrons are negative and I lost negative pieces of myself, I'm going to become more positive. Okay, so if I have like aluminum +3, okay, that means I lost 3 electrons. So now I have 3 more protons than I do electrons. Now an anion is negative. That means you gained electrons. So when you gain electrons and electrons are negative, you become more negative. So if I have like sulfur with a -2, that means I now have gained 2 more electrons, and I have 2 more electrons than I do protons. If you do not see a charge, normally your protons and electrons are just the same. Okay, it's only when the charge is there that will affect it. And we'll do some more of that later. All right, so number 5, it says, what do the numbers in the following symbol notation represent? Okay, so remember this top number here is your mass number, which is your protons plus neutrons. This bottom number is your atomic number, which is just your number of protons. Okay, and this right here is my charge, or it's called also an oxidation number. It just means that you are now an ion. That means you either lost or gained electrons. So just watch out for that. Remember, you're going to do the opposite, and we'll do more practice here in a second. You always do the opposite of what it says. If it's +1, you would minus for the electrons, and if it was negative, you would add for the electrons. Okay, what does the number in the following hyphen isotope notation represent? So we're talking about this 238 right here. That is your mass number. This is what I mean by that confusion that we're used to seeing is if you look on the periodic table and your mass number doesn't match the decimal number on the periodic table, that's okay because it doesn't have to. That is a specific uranium. It's called an isotope. Okay, you can have uranium like 238. 239. That is your mass number of that particular isotope, which is your protons plus neutrons. Okay. Now for this next part, I'm not going to do all these. I'll do a decent amount of them to kind of get the feel for it. Okay. If you want to, you can always pause this video and then you can try it and then play and then see if you get it right. Okay. So the first section's done for you. So we'll do the next section. So we have carbon 13. Okay, so if I want to do symbolic isotope notation, okay, I would need the symbol of carbon, which is just the letter C. Okay, now I'm going to do is I'm going to take this 13 right here because that's my mass number, and I'm going to put that on top. Okay, now my bottom number is just my atomic number, so you're going to look on your periodic table and see what is the atomic number of carbon, and that is 6. And so I'm done. That's it. Okay, you do not have to write a charge or anything like that. We would give you a charge, so we're not going to try to throw that at you. Okay, your atomic number is still 6, so that bottom number 6. Your atomic mass is the decimal one on the periodic table, so you have something like 12.011. Okay, so do you see how that 12.011 is not the same as my 13? That is okay, because we're talking about carbon 13 and carbon 13 only. Now my mass number is going to be 13, because I already gave you that. My protons is equal to my atomic number, which is 6. Now, if I do not see a charge anywhere, so if I look back here, do I see a charge on there? No, I do not. So protons and electrons are going to be the same, so it's going to be 6 and 6. Now, if I want to find neutrons, it is just going to be my top number minus my bottom number. So 13 minus 6 is going to give me 7 neutrons. And then I'm going to see, is this neutral, a cation or anion? Well, since I didn't have a charge, this is going to be neutral. Okay, moving on to the next one, I have 21383 Bi minus 3. So if you look up Bi on the periodic table, that is actually bismuth. So I'm going to write out bismuth. Okay, and I'm going to put bismuth dash 213. So I took that mass number and I brought that over here. So do not take the atomic number, take the mass number. So my atomic number will be that bottom number, so that's 83. My average atomic mass for bismuth, if you look on the periodic table, is 208.980. So if you notice again, it does not match my 213, but that is okay because I'm talking about bismuth 213. My mass number was that number on top, so that's 213. My protons is just my bottom number, which is 83. Now I do see a charge right here. I see a -3. Okay, so remember, this is where you're going to do the opposite of what you think. Do not -3 from your protons. You're actually going to add 3 because you gained electrons. You're more negative. So I'm going to have 86 electrons. Okay, my neutrons, I'm going to take the top number minus the bottom number. So 213 minus 83 is going to give me 130. And now I'm going to see, am I neutral, cation, or anion? Well, I have a charge, so I can't be neutral. So am I a cation or anion? So if I have a negative charge, the way I remember that is anion has an N in the middle, which makes me think of negative. So this is going to be an anion. Okay, let's look at this next one. So atomic number of 23. So we're going to look up 23 on the periodic table. Okay, and that is going to be vanadium. So I'm going to write out vanadium dash, and I gave you the mass number right here. So vanadium dash 50. Okay, so we're going to write our symbolic isotopic notation. So we're going to draw my V, because that's a symbol for vanadium. I'm going to put 50 on top, put 23 on bottom, and that is it. There's no charge or anything, so I don't have to worry about that. Now, my atomic mass for vanadium is 50.942. Okay, my mass number is already given. My protons is going to be my bottom number, which is 23. Do I see a charge anywhere on the vanadium? No, I do not. So my electrons are just going to be exactly the same. Okay, because remember, if there's no charge, that means you're perfectly neutral. You have the same amount of positives you do negatives. So 23 protons, 23 negatives. Okay, they cancel each other out, so therefore you're neutral. Okay, now my neutrons, I'm going to take that top number minus my bottom number. So 50 minus 23 is going to give me 27 neutrons. And I don't see a charge, so this will be neutral. Okay. We're going to jump down. We'll do the next one. Then I'm going to jump down to a positive so you can kind of see that. Okay, so 15.7 nitrogen. So N is nitrogen. Dash 15. Okay, my atomic number is the bottom number, so that's going to be 7. Okay, my atomic mass for nitrogen is going to be 14.007. My mass number is 15, which is that top number. My atomic number, my protons, is equal to my atomic number, which is 7. I don't see a charge anywhere, so my electrons are going to be the exact same, so 7. And my neutrons, 15 minus 7 is going to give you 8 neutrons, and then I don't see a charge, so it's going to be neutral. Okay, so hopefully you're kind of getting the gist of how to do this. I'm going to jump down here to a positive one so you can see what that's like. So I'm going to jump here to the 4420 Ca. Now Ca is going to be calcium, so I'm going to write out calcium dash 44. Okay, my atomic number for calcium is that bottom number, so it's 20. My atomic mass for calcium is 40.078. Okay, my mass number in this particular calcium is 44. My proton's gonna be my bottom number, so that's 20. Now my electrons is where I gotta pay attention. As you see that +2, that means I have more protons than I do electrons. That means I have more positives than negatives. So you're gonna subtract 2 from the 20. That gives me 18 electrons. Okay, neutrons still the same, top number minus bottom number, so 44 minus 20 is gonna give me 24 neutrons. And would this be a neutral, cation, or anion? So remember there's a T in the middle, kind of looks like a plus sign, so this would be a cation. Okay, now I do want to point out something is, what if you run into something like, I'm just going to write it down here. If you see something like Na plus or Cl with a minus and you don't see a number there, okay, that's like an imaginary 1. Okay, so if you don't see a number, it's just a 1. Also, you can write these different ways. If you see a Cl with a 1 and then a minus sign, it's the same thing. Okay, so it's just how people write it. So I just wanted to kind of show you that just in case you see that, so there's no confusion there. Okay, so now we're going to move on to average atomic mass, which is just kind of simple calculation stuff. So you would need a calculator for this. So what I would do is, now this is already in percentage form. Okay, so what I mean by that is you see that everything is already in decimals, so there's no need to move decimals at all. I give you all the chromiums. I give you chromium 50, 52, 53, 54. I give you their specific masses and their relative abundance. This is just the same as a percentage. So all I would need to do, let me go back to my pen, is just multiply across for each one. Okay, so 49.946 times 0.043500, and that would give you a number. Okay, I would do the same thing for the next one. Take 51.941, multiply across by 0.83800, and that would give you a number. You're going to do the same thing for each one of those. Just keep multiplying across until you get a number. Now, once you have all the numbers, you're not done yet. Okay, so don't stop at this step. Once you have all those numbers, you would add them up. Okay, so what I would do is once I have all the numbers, the answer ends up coming out to be 51.996 AMU. Now, a good way you can check yourself is look up chromium on the periodic table, and it should be pretty dang close. Okay, that's the way you can kind of check yourself. Now, on part B, this is what I mean by not being in decimal form. It says find the average atomic mass of iodine if it consists of 80% iodine 127 and 17% iodine 126 and 3% iodine 128. Okay, so what I'm going to do is I'm actually just going to take each mass and multiply it by its percentage. So iodine 27, so iodine is just I. Okay, and I'm going to keep it nice and organized, so 127 on top. So I'm going to take that 127. I'm going to multiply it. Now this is where you got to watch out, is you notice how 80% is a big number. If you take 127 times 80, you're going to get a really big number. Okay, so you're not in decimal form yet, so I'm going to move that decimal to the left by 2. 1, 2. So it's going to be 127 times 0.80. Okay, and that will give you your number. Yeah, now the reason is because I have the key in front of me and stuff, I don't have each individual number. Okay, so that's why I'm just writing down the number symbol. Okay, so now I'm going to jump down to the next one. I have iodine 126. Okay, I'm going to take that mass, which is 126. I'm going to multiply it by its decimal form. So either divide by 100 or just move the decimal left by 2. So 1, 2. So that's 0.17. Multiply across, and I get a number. Okay, and then I have my last one, iodine 128. I would take that 128, multiply it. Now I have 3%, so here's where you gotta be careful. So I'm gonna put this over here. So if you have 3%, I'm gonna move this decimal that would be right here to the left by 2. 1, 2. Now if you have an empty space, fill it with a 0. So just watch out for that because that can lead to a mistake. So it's actually 128 times 0.03. And you're gonna get a number. Now once you have those numbers, you're just gonna add them all up. Okay, and your answer for this would be 126.90 AMU. Okay, if you look up iodine on the periodic table, it should be pretty close. So 126.904 on the periodic table. Yeah. So those are fairly simple. Just make sure if it's not in decimal form, just make sure you move the decimal left by 2. Okay, now I'm going to talk about the types of radiation. Okay, we have alpha, beta, gamma. Okay, so for the symbols, okay, most people are going to use a 4,2 helium. If you want to use the little fish symbol for alpha, you totally can. There's nothing wrong with that. You can do, for beta, it's going to be a 0 minus 1 E. Okay, or you can do the fancy little B with a little tail. Does not matter. I'll accept either one. And then gamma is going to be your 0, 0 with a Y. Okay, so those are your symbols. So if you see those, one, you need to make sure you know them. So that tells you what type of decay it is. Now your charge for this would actually be a positive or a +2 for alpha. We just know that alpha is positive. It has 2 protons with it. Now beta is actually going to be a -1 charge because you're firing off a negative electron. Okay, and gamma has no charge. It is just neutral, meaning it does not care if you introduce any type of magnet to it, it's not going to be attracted to anything. Okay, your mass for alpha would just be 4 AMU because its mass number is 4 because that's helium. Okay, beta, it has mass, but in this case it's 0 because remember it's an electron, so it's just negligible. It's too small. It won't really affect us. Okay, and gamma is just pure energy. There is no mass. There is no particle to actual gamma. Okay, now as far as penetrate, that just means the ability to go through something. So even though alpha is the biggest, it's like the slowest. So it has a low penetration. Okay, the way I explained this to my class was think of it like a basketball. It's big, but basketball is easy to stop. Now versus a beta, this one's gonna have medium. Okay, it takes a little bit more. Okay, and I can go back to alpha real quick. A simple paper can stop alpha. Okay, so it does not take much. Now beta, think of it like a baseball, like 110 mile an hour fastball it's coming. Okay, so it's got more energy, it's smaller, so it's gonna take a little bit more to stop it. So a sheet of aluminum can stop that. Now gamma is gonna be that is your, no joke. Okay, that is gonna have a high penetration. Okay, it takes thick lead to be able to stop that. Okay, so think of that as like your high-speed bullet. Now beta, so electrons are moving fast. Now these are all moving fast, okay, but not in the way we're thinking of. Like our terms of speed versus their terms of speed is a little bit different. So they're all moving fast, just relative to each other. Gamma is moving extremely fast. It's small, like it's just energy. Okay, so it takes thick lead to be able to stop that. Okay, as far as energy goes, same thing. It's going to follow the exact same. It's got low energy for alpha. Beta's got medium energy. Okay, and then gamma has high. Now, as far as illustration goes, it's pretty much just drawing. The key just shows you a drawing of alpha stopped at paper, beta being stopped by lead, or I'm sorry, aluminum, and then gamma being stopped by lead. Okay, what I do care about is what if I had different particles? So what if I had alpha moving along, and up here I have a plate. I have a positive plate, and here I have a negative plate. Okay, so these are my magnets. So if I have an alpha, so say it's positive, okay, I'm going to see what happens when I get near these plates. Okay, so if I'm a positive, I don't like positive, but I'm attracted to a negative. So alpha is actually going to start moving towards the negative magnet. Okay, so now what if I go back and I have a beta coming through? Okay, so these are my negative particles, and it's going to come to this magnet. So it's not going to like negative, but it's going to like the positive, so it's actually going to go toward the positive magnet. Now what if I have gamma come through? Gamma has no charge, so gamma is not going to care about any of this stuff, and it's just going to go right on through. Okay, so that's the best illustration for gamma, is to see how their charges are attracted or affected by something else. Okay, fusion and fission, this won't take long to do because this is just a simple Venn diagram. Okay, so we're going to talk about both of them. So fission, remember, is when you break something apart. So okay, you're going to break from large into small. Okay, so you take a big atom, you fire a neutron at it, and you break that into pieces. Okay, it releases energy, and then the neutrons from that atom goes on, breaks apart another atom, and causes a chain reaction. Okay, it is also highly radioactive. Now, it does produce energy, but the downfall of that is it does produce radioactive waste, which is not very good. Okay, and we actually use this in power plants and bombs. Okay, bombs are just basically an uncontrolled fast chain reaction that you can't stop, and it leads to that explosion. Okay, versus fusion, this is when you have small atoms form into big atoms, and they're not very big, but compared to what it was, it is bigger. Okay, so this is when you have like a hydrogen and a hydrogen, they come together and they make a helium. Okay, so that is fusion. That's what's happening in the sun right now. So this is what happens in the stars. Okay, and it is not radioactive. So it's just producing helium, so there's no bad effects coming from it. Okay, so fission is to break apart large and small. Fusion is to take small and combine into big. Okay, and it is only with hydrogens coming into heliums. Now, what do they have in common? One, they are all nuclear reactions. Okay, so you have reactions going on. Two is they produce a large amount of energy. Now, I will say this, fusion does require a lot of energy. Okay, it takes a lot of heat and energy to be able to force hydrogens that don't like each other into coming together and to become helium. Okay, the sun has that ability. Okay, we're kind of starting to scratch that surface a little bit. And they are both highly exothermic, meaning they produce a ton of heat. Okay, so like when you step outside, you can feel the effects of that when you get in the sunshine. Okay, so that was the difference between fission and fusion. Okay, we'll do some examples real quick. I'm going to scroll down here to the bottom real quick just so we can keep talking on fission fusion. So if you look at 14, it says identify each of the following as fission or fusion reactions. Well, if I have a hydrogen and a hydrogen coming together to make helium and produce energy, okay, this has to be a fusion. Uh-oh, there we go. So anything coming together to make something bigger is going to be fusion, and it has to be hydrogens and heliums. If you see a carbon in there anywhere, that is neither. Now, if you take B, you have a 235-92 uranium, and you have this neutron being fired at it. Now, if you noticed, my uranium was broken apart into two pieces, because if you add those bottom numbers up, 38 and 54, you should get 92. So that means you still have the same number of protons as before, but now you've split it into two different atoms. Okay, and you also produced more neutrons to go off and hit other atoms and break them apart. So this is fission. Okay, C, you have hydrogens coming together to make a helium, so making it small into big, so there's going to be fusion. And D, I have plutonium and a neutron, okay, being collided, and it breaks into pieces, so this is going to be fission. Okay, now last bit, we'll go to the decay equations. Okay, number 10 says, how are the mass and atomic numbers of an isotope nucleus affected or changed in each of the following processes? Okay, so if I get rid of a 4,2 helium, okay, my mass would go down by 4 because I lost 4 mass number. Okay, my atomic number, so my atomic number would go down by 2, okay, because I lost 2 protons. Now beta decay is a 0 minus 1e, so if I lost that, my mass really wouldn't change. So mass not changed. Okay, now if I lost something negative, I'm going to become more positive, so my atomic number is actually going to go up by 1. And gamma is going to be your 0, 0y. If I lost that, I'm not losing anything, I'm just losing energy, so my mass not changed, and my atomic number not changed. Okay, so let's do some examples down here. So I have a 222-86Rn. Okay, treat this arrow like an equal sign, and it also needs to be like a wall. Okay, please be careful in how you do this math. You cannot combine, you cannot mix left side and right side. So if I want to figure out what this space would be, I would need to know what plus 2 would give me 86. Well, this would have to be 84. Okay, and then on the top number, I would say what plus 4 would give me 222, and this would give me 218. So then what you do is if you look on the periodic table, you look up number 84, and now that is polonium, so PO. Okay, so remember this bottom number tells you who you are, so if that changes, you've changed into another atom. Now, this 4,2 helium is a dead giveaway that this is alpha decay. Okay, my next one, I have a 221-82 lead, PB. Okay, there's my equal sign. Okay, so remember I cannot mix left side, so this is where you gotta be careful. What I do is, what I see students do is they do 82 minus 1, and they would put an 81 on bottom. Okay, now if you were to recheck your math on the right side, would 81 minus 1 equal 82? No, it would not. Okay, so we're actually gonna get rid of that. Okay, so I would have to see what minus 1 would give me 82. So this would actually be an 83 on bottom. Okay, and then 0 on top, so that means mass is not going to change, so I'm going to keep that as 221. Now I'd look up 83 on your periodic table, and that is bismuth, so it's Bi, and there's your answer. Now when I see this particle right here, the 0 minus 1e, that is a dead giveaway, this is beta. So again, please make sure you check your math. Don't mix sides. So don't take 82 minus 1, because when you do that, you are mixing sides and it led to the wrong answer. So you had to see what minus 1 would give you 82. Okay, so same answer here on C. Okay, be careful. Don't do 14 minus 1 and put 13 on bottom. Okay, that won't give you 14. So what I would do, sorry, is I would take what minus 1 would give me 14. So that'd be 15 on bottom, 0 on top. So my mass isn't going to change. So 27 plus 0 gives me 27. Look up 15 on the periodic table, and that is phosphorus. And there's my answer there. And I see a 0 minus 1 E. That's beta. Okay, so hopefully you're kind of getting the gist on that. So we're going to go down here and find a gamma one. Okay, so at F, I see the 00Y, so that's a dead giveaway, that's gamma. Okay, so nothing's going to change, so 26 plus 0 gives me 26 on bottom, 58 plus 0 gives me 58 on top, and 26 is still iron. So nothing changed, it's just the gamma particle. Okay, so moving on to the next section, this is the part where you have to actually write out the entire equation. Okay, I'm just going to do, I'll do one from each so you can kind of see what it's like. So carbon 14, first thing I need to do is I need to fix that and put it in isotopic notation. So I'm going to take carbon, which is C. I'm going to put 14 on top. Carbon has the atomic number 6, so I'm going to put that on bottom. Okay, so this means this carbon is unstable, so I'm going to draw my arrow right here. Okay, so remember there's always one thing on the left side. Okay, so don't do your plus sign and everything on the left side. There's only one thing on the left because this carbon is unstable, so it's going to decay into products. Okay. So this is going through beta decay. So I'm going to do a 0 minus 1E, because that's my beta particle. Plus, now I need to figure out what's my missing piece. So again, check your math. If you need to, draw a wall right here. So what minus 1 would give me 6? That would be 7. What plus 0 gives me 14? That'd be 14. And if you look up 7 on the periodic table, that is nitrogen. And that means I am done. There's my answer. There's nothing else you need to do. If you need to check your math, you can. Now, a couple of terms I want to talk about is on the left side of the arrow, this is called reactants. And we'll get into more into that in other units. And this side, this right side, is called products because you are producing something different. Okay, so that is a simple beta one. So let's go down to alpha. Okay, I have radium-222, so I'm going to fix that. So radium is Ra. And I'm going to put 222 on top, and I have 88 on bottom. Now it says alpha, so that means I'm going to jump off of 4,2 helium, or if you want to use that little alpha symbol, you can. Plus, now I'm going to draw my wall just so I don't mix things up. So what plus 2 would give me 88? That would be 86 on bottom. What plus 4 would give me 222? This would give me 218. And 86 is now going to be Rn. That is your radon. Okay, and there's my answer. Everything's done. Don't need to do anything else. Okay, so hopefully this video kind of helped you out. If you needed it, please feel free to go back and watch anything you need to and let us know if you need anything. Thank you for watching.